you think would be particularly useful to talk about first? If not, I can just grab one and we can go over those.
I think we're good with you, going ahead and grabbing one.
Cool. Let's do number 10 first. And I'll go ahead and I'm going to call in with my iPad so I can do some note taking. Yeah, go ahead and in the meantime, while I'm getting this set up, go ahead and look at number 10 and think about how you would get started with that. All right, so this number 10. The integral of 5x times the cosine of 2x dx. All right, so what method should we use here?
Undoing chain rule.
Okay, undoing chain rule. So if you want to undo chain rule, basically we have to think about an inner function and an outer function. So just to remind you, looking at how to take the derivative of a composite function. We have this. So now basically what we want to do is go the opposite direction. So now what we have to have is, do we have a composite function? Do we have something that looks like the right-hand side of this equation that we can take an antiderivative of? So what would you say our f prime of g of x is? Or actually, it's probably easier to look at this. We have a g prime of x.
No, we don't.
No. In fact, I don't think that chain rule is going to work here. If I make it, what's a one change I can make to this function here that would allow chain rule to work for me?
Make it cosine 2x squared.
So yeah, that's one way. Oop, that's what I wanted. If I had cosine 2x squared, then yes, the derivative of cosine 2x squared would give me, as part of it would give me a 4x, so I'd have a constant multiple there. Another thing that maybe some of you were thinking is if that x was not there, then I'd be okay to do chain rule. But chain rule is not going to work here. So what method should I look for instead? Ash says product, Shannon says product. Let's take a look at that. So let's just remind ourselves of how that works. So if I take the derivative of a product, you're going to wind up with something like this: f prime g plus fg prime. So basically, if I want to go the opposite direction, let's just say one of these is going to be hard and the other one's going to be easy. And basically, I'm going to try to solve this equation for the one of these integrals that's going to be hard to do. That way, basically what you're doing when you're undoing the product rule is you're trading a difficult integral for one that's not that hard, for one that you can actually do. So from here, I have f prime of g is going to be equal to the derivative of fg, not plus, minus fg prime. And then from there, if I integrate both sides, I get integral of f prime g equals fg minus the integral of fg prime. So now basically what we want to do is split this 5x cosine 2x into parts here. One of those parts I'm going to take a derivative of, and the other one of those parts I'm going to take an integral of. So what should I call f and what should I call g? So Allison is giving me f prime equals 5x, which would make g cosine 2x. So basically, if we're calling f prime 5x, that means we want to take the antiderivative of it, right, to get f. What would that make f equal to? Got 5 halves x squared. And how about g prime? What's the derivative of cosine 2x? I have negative sine 2x. Do we agree with that? I got 1/2. Okay, so now remember to follow the chain rule for these things. We should have a negative 2 sine 2x. So now that we have that, let's start filling in the right-hand side of this, this equation here. So fg is going to be 5 halves x squared minus the integral of f, which is 5 halves x squared, times g prime, which is negative 2 sine 2x dx. All right, how do we feel about where we wound up? Can we now do this integral?
I had a quick question. Why is fg only 5 halves x squared and not also cosine 2x multiplied by that?
You're talking about the f up here? The F
No,
prime?
I'm saying like when you plugged in what we evaluated on the right hand side into fg minus the integral of fg prime, you just said 5 halves x squared.
Yeah,
for
that's a
fg.
good catch. Good catch. Thank you.
Oh, okay.
So 5 halves x squared cosine 2x. Yeah, thank you for that. So now is this something we can do, this integral here? So Jerome is not sounding like this is the right way to go. So, right, so us taking the antiderivative of 5x made this more complicated. So let's start over. Let's say instead f prime is equal to cosine 2x and g is equal to 5x. Now, if I have cosine of 2x being being the derivative, what would f be equal to? Ash says 1/2 sine 2x. We agree with that?
Yeah.
There you go, 1/2 sine 2x. And what would g prime be?
5.
5. Cool. So now let's redo this. So the integral of f prime g equals fg minus the integral of fg prime. So that's going to be fg 5 halves x sine 2x minus the integral of f prime or fg prime 5 cosine 2x. So the integral we have left now, is this one we can do? If so,
How come it's 5 cosine 2x and not half sine 2x?
okay, I'm glad you guys are catching me because I keep missing these. So yeah, it should be fg prime not f prime g prime. All right, so that should be 5/2 sine 2x. Okay, that should be good now, right? All right, so now what is the antiderivative of this thing on the right?
Five over four cosine 2x
5/4.
with a negative.
Oh, negative. Okay.
So, yeah.
Okay. Yeah, that's good. So final result here, 5/4 cosine 2x plus c. One thing I want to point out here, because I think this might make things a little easier to think about, because it seems like when I asked you what the antiderivative of cosine 2x was, seemed like a lot of people were confident in that one and were pretty quick with it. Not so much the case for this one, the last step we did here. So one thing I want to remind you of is this. I can take that antiderivative and rewrite it like this: 5/2 times the integral of sine 2x. So whenever you have a multiplied constant like that, you can pull it out of the integral and basically take that integral and then multiply it after the fact. So always an option you have if that's something that'll just help you unclutter your thinking. Gabriella says, isn't the formula for undoing the product rule the integral of fg prime equals fg minus the integral of gf prime? So that is, I think that might be the way that Mark has done this, but one thing let's just go back and look at this. Look at the way the product rule works for differentiation. Basically, I am taking the derivative of one and multiplying it by the other, and then I'm going to add that to the derivative of the other multiplied by the first one. So it's very symmetric. All I'm doing is I'm multiplying and adding, and both of those operations I can do in whatever order I want. So I can compute this term on the right, then compute this term on the left, and then add them together. I can do it in any order I want. And because of that, sure, the way I developed it right now was the integral of f prime g equals fg minus the integral of fg prime. I could have easily solved that out to be the integral of fg prime is equal to fg minus the integral of f prime g. And those of you who are looking at integration by parts, that's probably the way it looks in there. And if that's the way you want to look at it, that's fine. But really, knowing that this and this are totally symmetrical, and I can call whatever I want f and the other part g, I have full choice over that. It doesn't really matter which way I make it look. So whichever way makes more sense for you is totally fine. And like Ash says, doesn't really, you're naming f and g whatever you want. Like in this case, and for this problem, we didn't make the best choice at first. So I didn't rearrange this formula here. I just renamed f and g. But yeah, those of you who are more comfortable with looking at it as the integral of fg prime, yeah, you're totally fine to do that. All right, that was number 10. Good integration by product rule example. Anything else on here jump out at you that we should take a look at? Allison wants to go over a partial fraction example. We can definitely do that. I'll try not to do the one I did last hour. Let's look at number 12. So 12 is the integral of 2x plus 3 over x times x squared minus 6x plus 9 dx. Okay. So what's a good first step to take here?
Factor the x squared minus 6x plus 9.
Good. So yeah, the denominator is partially factored, but let's keep going here. What does that quadratic factor into?
X minus 3 squared.
X minus 3 squared. Good. All right. So from there, now we can, and you'll notice I am not writing this as an integral right now, because we're not going to be dealing with the actual calculus of this, the actual antiderivative, for quite a while. Right now, I just want to rearrange and rewrite this function. So from here, now that I have it totally factored, I can decompose this into partial fractions. So what are those fractions going to look like?
Would it just be x minus 3, and x minus 3?
So you were a little quiet, but this is what I think I heard. How do we feel about that? So Ash and Gabriella are wanting to modify this for having one of these terms be squared. Now, how do we feel about this? Okay, this is good now. So now, for those of you who, this kind of hits on something I sent that email about yesterday. Doing an example like this, I think people see the resemblances to this and cross multiplying, when really that is mostly coincidental. That's really not what we're doing here. What we're really doing is, I want to multiply this entire equation by that common denominator, and that helps me clear all the fractions out. So I'm going to multiply the left by x times x minus 3 squared. So this cancels. And over on the right, you're going to get some cancellation, but you're also going to get some other term showing up. So this is going to be bx, x minus 3, and this is going to be cx. So if we write that out a little cleaner, we get a times x minus, the left-hand side here, 2x plus 3 equals a times x minus 3 squared plus bx, x minus 3 plus cx. All right, where do we go from here? Okay, let's distribute through all the brackets on the right-hand side. So this becomes x squared minus 6x plus 9 plus b x squared minus 3x plus cx, ax squared minus 6ax plus 9a plus bx squared minus 3bx plus cx. And one more time, let's just group all these things together. So my x squared terms are a plus b. My x terms are negative 6a plus b plus c. And my constant terms are 9a. It's really just 9a. Okay, I guess so. All right.
Steve, I think it's for x, the terms for x is minus 6a plus 3b.
Yep, or minus 3b, right?
Yeah.
Okay, thank you for that. All right, so we know from here, Ash is saying a plus b equals 0. Why does a plus b equal 0? How are we making that conclusion?
Because on the left-hand side, there's no term
Right.
for.
So yeah, we're not going to have a quadratic term here. So I'm going to kind of shoehorn in this 0x squared because that's really the conclusion we're making. So we have these three equations: a plus b equals 0, negative 6a minus 3b plus c equals what? So what should be on the right-hand side of these equal signs for, okay, I see 2. And the bottom one should be 3. And as far as systems of 3 equations go, this one's pretty friendly. So you get for free that a equals a third. And then from there, you know that a and b have to be opposites. So I'll get that b equals negative 1/3. So now we have this negative 6 times a, which is 1/3, minus 3 times negative 1/3, plus c equals 2. So I get negative 2 plus 1 plus c equals 2. So c equals 2 minus 1 plus 2. Are we okay with c equals 3? Okay. So now from here, like so far, nothing we've done has anything to do with calculus or taking an antiderivative. But now we can rewrite this so we can. So, and we'll just split it up since we have decomposed it now. We know that a was a third. And this is going to look a little strange, but I think it helps with making sure that you're keeping organized. I think it actually makes the antiderivatives easier. The second one, Ash, I really do have negative 1/3 because I just took the negative sign out of the integral. And then plus 3 over x minus 3 squared. All right, so now from here, we can take the actual antiderivatives. So let's just take it one term at a time. What's the first one going to be? Okay, I see some votes for 1/3 natural log of x. All right, so, or someone says natural log of 3x, which that also, they don't look like they're equal, but that actually is correct as well. One thing that I'll kind of reiterate my hint from before, you can actually pull these out if it makes it a little easier to digest. So first one should be 1/3 natural log of, and just to be clear, absolute value of x. I have a feeling some of you have bumped into that on the iMath stuff for this concept. This one is very similar, 1/3 the natural log of the absolute value of x minus 3. And this third term, what's this third term going to look like? Is this last one going to be a natural log? Okay, I got to vote for no. So how can we handle this last one if it's not going to be a natural log result? Okay, let's see some votes for 1 over x minus 3 to the negative third power. So that's one thing I'll kind of rewrite this up here. This is just if you rewrite this, it might make it more clear that you're looking at a product rule situation. So I remember add 1 to the power. So that's going to become 3 over x minus 3 plus c. Any questions about that one? And Jerome, it is undoing the chain rule. But it's one of these cases where I'm guessing that many of you can handle that one without really going into defining what f prime is and what g is and all basically building it up. Yeah, you're not wrong that that's what that case is. Any other questions about this example? All right, so we've done what was the first one we did? Integration by parts, or yeah, undoing the product rule. We did a partial fraction example. Let's do one where we have to get a trig identity involved. So let's look at number 17. 17 is the integral of sine to the 5th x cosine squared of x. All right. How should we get started here? Ash is saying product rule. All right, so let's think about this. How would you set up product rule? So I'm going to follow you all. It seemed like most people were saying they liked this look of the undoing the product rule. So then we're deciding basically part of this is f, part of this is g prime. Which part of this should be f? Okay, I got to vote for cosine squared, which means g prime is going to be sine to the 5th of x. What is the derivative of cosine squared of x? So this might not be obvious, but this is actually a chain rule example because cosine squared of x is really the same as this. You take the cosine of an angle and then you square that. So basically chain rules say I would do, 2 cosine x, but then I have to take the derivative of the inside. So you end up getting -2 sine x cosine x. But then this integral of sine to the 5th of x, we don't actually have a way to do that. So a couple things I want to say about this. Product rule is not going to work for this one. And in general, product rule, most of the time you've seen product rule work And I think every time that we've used the product rule, you really have to use it to make your function somehow simpler. And in this case, taking the derivative of sine to the fifth or cosine squared you're not going to really reduce powers. You're not really going to, I mean, basically you traded cosine squared for something involving sine to the first and cosine to the first, but it didn't really get any simpler. And in fact, integrating sine to the fifth of x is not something we can do directly. So product rule is not going to work here. So Layla's asking if we can split them into two. Because they are multiplied together, you cannot break them apart. So I cannot say that this is equal to the integral of sine to the fifth x dx times the integral of cosine squared x dx. Gabriella is saying use trig identities. So that's what we're gonna have to do. And I'm kind of giving you a little bit of a teaser for tomorrow, because I believe that Mark is going to spend most of the day on, how to use practicing using trig identities to break these things down. So specifically, what trig identities do we think would be helpful here?
We could convert cosine squared of x to 1 minus sine squared x.
Okay, so just to highlight this, the identity he's talking about using is cosine squared of x plus sine squared of x equals 1. So because of that, we can do this. We can replace cosine squared of x with 1 minus sine squared of x. And then I can break this up into sine to the fifth of x minus sine to the seventh of x dx. Is this an integral now I can break up into two smaller integrals?
Am I missing something? It's to the seventh power? Or the second?
Because so I transformed this cosine into 1 minus, so this cosine squared of x into 1 minus sine squared of x, right? So now, if you distribute that sine to the fifth,
Gotcha.
you have to add the powers there.
Can you say that again, please?
Sure, and I'll give you an analogy here. So remember, when you have something like sine to the fifth of x, really what that means is I'm going to take the sine of whatever that angle x is, and then I'm going to raise that to the fifth power. So this is kind of like, if I had y to the fifth times 1 minus y squared, you distributing that is just the same as you adding the powers, right?
I get it now. Thank you.
Okay, good. All right, so, and it sounds like a couple of you are saying that, yes, you absolutely can break these down. So when the integrals are multiplied by each other, it is not permitted for you to break them up. But when they're added together, and you can kind of relate this back to when you were doing derivatives, if you have if you have a function, 4x squared plus 3x, I think just by now, when you take a derivative of that, you just instinctively take that one term at a time. But if I had the integral, let's say I had the at x squared, but really I wanted to think of that as x times x. So I just take the derivative of x, that's 1. The derivative of x is 1, so obviously that doesn't work. So when they're multiplied together, you're not able to break them up, but when they're added or subtracted, you can definitely do that. So do we have a way to integrate sine to the fifth of x or sine to the seventh of x? And I think now you're getting the suspicion that or yeah, this is not going to work. So we do not have a way to integrate sine to the fifth of x. Let's say I wanted to undo the chain rule here. What's something I could have multiplied by sine to the fifth of x that would make chain rule work for me? Yeah, I got to vote for cosine x. So yes, the integral, so the derivative of sine of x is cosine x. So if I had a cosine in there multiplied, then I'd be okay. But I don't have any cosines left. Basically I traded both my cosine squares for a 1 minus sine squared. So I really think that it was a good idea to use the identity that we have written off to the right here, but I think we have to use it elsewhere. So instead, let's do this. First, I'll rewrite this as sine squared of x, sine squared of x, sine of x, cosine squared of x. You know, just in the interest of time, I'm going to modify this to be sine cubed. There's a point where this would go from a good teachable example to just tedious. All right, so we said that if I had sine to any power and had a cosine with it, then we could undo the chain rule. Would that still be true if we went the opposite direction? So let's say now, instead of transforming cosine squared, we transform sine squared. So we get 1 minus cosine squared of x times cosine squared of x times sine squared of x dx. Do a little distributing, we get cosine to the cosine squared of x minus cosine to the fourth of x times sine. Oh no, this is just fine. So I got a good question from Ash here. Why can't we keep three sine and 2 cosine? Why do we have to change it? So for undoing the chain rule, basically what we have to have is this. So I'll put this out again. The integral of some composite, or the derivative of some composite function, is going to be f prime of g of x times g prime of x. So if we were to leave, you know, both of these sine and cosine to some power greater than 1, we would not be able to get that to fit this, fit our chain rule here. And that all comes down to this g prime of x component. Basically, our end goal is going to be to have our, you know, our outer function be x to some power, and our inner function be either sine of x or cosine of x. But if I do that, then g prime of x is going to be either cosine of x or negative sine of x. So that doesn't really give us any flexibility with our derivative being raised to a power. So I really have to get one of these sine or cosine, I have to get down to a power of 1. Rodolfo is asking, where did the negative cosine of the fourth come from? So that all comes, and I'll just underline it in blue, maybe slightly less dark. So basically this, let's bring this down over here. And instead of cosine, let's say this, y is equal to cosine of x. If I make that little substitution right there, I can do 1 minus y squared times y squared. And then it's just a matter of distributing the y squared, so I get y squared minus y to the fourth. So Ash, if you're saying that f prime is equal to the cosine to any power, I think we saw, I wish I hadn't erased it now, but you know, we saw what we had when I had when I tried to take the antiderivative of sine or cosine raised to some other power. You know, if the power was simply squared, which in this case we might be able to do it, but it would be pretty complicated. You could use one of the half-angle trig identities. But in the case we had, you know, before I modified this problem, we had sine to the fifth, which you just can't do directly. So, right, Rodolfo, the cosine squared was just distributed. All right, so Ash, let me go on. Hold that question, Ash, because I think it's about to. Hopefully, I'm about to make clear why this will work. So now I'm going to split this up into two different integrals, and I'll give myself some room. I have cosine squared of x sine x dx minus the integral of cosine to the fourth x sine x dx. So let's just focus on one of these at a time. So the one on the left, I have cosine squared of x times sine of x dx. Is this something I can undo the chain rule to help me with? I mean, if you look at this this stuff right here, I've kind of given myself a wish list. Do I have a g prime of x that looks like cosine or negative sine? Okay, so let's go with this. Really what I have is negative sine of x. So if g prime of x is negative sine of x, what is g of x equal to? Okay, I'm seeing some votes for cosine x. And is there a number I could fill in here? Do I have, so if I have cosine x as my inner function, have I raised that to a power? And the answer is yes, I've squared it. So now basically what I have is I have cosine squared of x times negative sine. So one thing I'll do here is this. I really want this to be negative sine, right? So, and I don't really think that Mark has done this way, but I can put a negative sign, just like you can pull out constants from integrals, you can put them in. But in this case, to keep everything equal, I'm going to multiply the inside of my integral by -1, which means I have to multiply the outside by -1. And hopefully now, many of you are seeing it looks like at least one person has typed this in, that I'm going to have -1/3 something to the third, right? And that something is my inner function g, which is cosine of x. Based on that, can you tell me what the term on the right would become? I have a vote for -1/5 cosine to the 5th of x. I think I have a little bit of a change I need to make here.
Would it be +1/5?
It'll be +1/5. Because really, if I really want this to match exactly, you know, my derivative, strictly speaking, is negative sine of x dx. But in order to make that negative on the inside of the integral, I have to switch the sign on the outside. Any questions on this one?
I had a quick question for earlier in the problem. You said you were getting rid of some of the busy work because we were dealing with sine to the fifth.
Yeah.
But going like higher up in the problem, we're just kind of left with sine cubed cosine squared. So did you fundamentally change the problem there to
I
get rid
did.
of?
Yeah.
Okay,
Yeah.
gotcha.
So yes, I did not do question 17. I modified it so we wouldn't be here for another 10 minutes or so.
Gotcha. So
Yeah,
in
so,
reality, there
but-
would be another sine squared left over.
Yeah, and there'd be more than that left over.
Gotcha.
So really it would have been like 10 or 12 more minutes of work and I really wouldn't have been able to teach you anything new. Okay, yeah, Ash, you're right. And Ash says, and this is, I want to highlight this for all of you. I get how this works, but I don't think I'll be able to do it on my own. That is probably true for the majority of you all right now, if not all of you. But there are a few days left. And I think I would really recommend you do a couple of things before I sign off today. So this sheet of antiderivatives, and I don't mean to call anybody out here, but I'm guessing that since nobody had any really specific wishes for me to work anything out on here, that meant that many of you haven't looked at it. So I would definitely rectify that. And if I'm wrong, I'm sorry. But if I'm right, I would definitely go through here and at a minimum, make sure you know what the right plan of attack is. But I would also encourage you to work out many of these. Because a lot of this, this all comes with practice. So I believe if, most of you, if you had 4 hours and the test was given to you right now, you could do all these antiderivatives, but that's not going to be the case. So it really is going to benefit you to figure out, or how do I recognize when I'm undoing the chain rule or where I'm doing the product rule, or when I have to do partial fractions, or if it is partial fractions, do I know how I'm going to break it down? So all those things come with practice. So definitely work some of these out. And also, I'm going to post this video. I'm going to go ahead and stop recording now. I've already posted the video from